Mute. Hi all, welcome to the algorithms final presentation. We are going to discuss about finding optimal solution for traveling salesman problem. And we are team members of Chandra Teja and Rajesh and Sai Vinith Kaza. So traveling sales problem is the problem when we have to find the optimal. There will be a salesman and there will be given a list of number of cities, and the salesman have to go through all the cities and come back to the same starting point, and we have to find the minimum path. That is the traveling salesman problem. And as there are a lot of routes, and we have to find the shortest and efficient route, this problem can be a lot of this problem can be a very challenging problem, and it is easy to discuss the problem, but solving the problem might be a lot difficult. And that's the reason why this TSP problem can be considered as NP-hard problem. So while going through this problem, we felt like what are the different algorithms can be used, and what is the efficient or effective, and that comes close to the optimal solution. And that's how we pick this project. Next. So yeah, TSP is a basically NP-hard problem. So while doing brute force, it can be solved. Uh, it can be solved, but the time complexity will be a big issue. But yeah, so basically 10p hard cannot be solved in polynomial time as easily as other problems. So it is NP hard problem. Next. So to solve TSP, we picked 6 algorithms, and out of the 6 algorithms, there are basically 3 types of those algorithms. So exact is basically the naive approach, that is the brute force algorithm. Heuristic is the nearest neighbor algorithm, greedy approach, and genetic algorithm, and approximate algorithms of 2-approx using MST and the Christopher algorithm. So we can pick the algorithm up to our choice based on the solution that we want. Like if we want optimal solution, we will pick the exact approach, and or if the input size is low, we pick the brute force again. And if but if you pick the exact approach, the time complexity will always be an issue. And if you need an optimal or approximate solution, you need to go for approximate things. Or if you want like a greedy approach or something, you can go for the heuristic one. Next, please. So for this project, we got the data set from TSP world countries. The link contains like around about 25 countries, and each country has around like thousands of cities, out of which we picked one city that is called Djibouti, and that has around 38 cities. And the data set is basically that comprises of X and Y coordinates of all the city nodes. And we basically took we manipulated the data into a adjacency matrix with Euclidean distance to feed it into the data. And yeah, next please. So name approach. For TSP to calculate the brute force algorithm, first we start with the starting node. We take one city as a starting node, and we take all the remaining possible routes. We do all the permutations in the formula of n-1 whole factorial. They are generated, and we calculate the distance for all these paths. Out of these paths, we take the minimum path, and that will be the solution, minimum required solution for the naive approach. So as this is happening in n-1 factorial times, and we're iterating over all the nodes again, so it will be happening overall of a n factorial time. And greedy approach is the algorithm where it is like a small, better and optimized version of the naive approach. The main thing of greedy is, we find a local optima during the solution, and then try to reach to the global optima of the solution. So that's how we approach with greedy as well. We have all the list of the weights of the edges, and we sort all the edges. We start with a random node, then we update the tour with the smallest near. We take a node, then we update the tour with the smallest distance edge, and we have to keep updating the tour until all the nodes are covered, and then return the tour with the smallest distance. And even for greedy approach, it will be the time complexity will be n square log n, where the time complexity will be n log n for calculating the minimum distance node, minimum distance edge, I'm sorry. And as we have to iterate over n times for all the iterations, it will be n square log n. And it will be continued by Rajesh.
So yeah, nearest neighbor algorithm. So basically, the main idea here is we select a city first, randomly select a city. We then go to the next city, which is the next, the next nearest city. And from the next, from the second city, we'll just go to the nearest one. And this process is basically repeated until all the cities are visited. That's what I explained here. The idea here is to start with a random city, and visit the nearby ones until we visited all of them. So this is a greedy algorithm variant. So the pseudocode is also the same actually. We start with a vertex and make it as the current node. We examine all the other nodes and we examine all the unvisited nodes and select the next nearest one. We repeat this process until all nodes are selected, and then we print the part and we calculate the distance. So, as for the runtime of this algorithm, uh, basically we select a city and we check the Euclidean distance with all the other cities, right? And this process is will be repeated again n times. So the time complexity, I mean, uh, we are actually selecting with the unvisited nodes, but still the worst case time complexity will be big of n square. Two approximation algorithm. Two approximation algorithm basically runs with basically follows triangle inequality, and it works. This continues with Prim's MST algorithm. So the idea here, okay, let me start with triangle inequality first. So basic distance of AB will always be less than or equal to distance of AC and distance of CB. I mean, distance between two nodes is always less than distance between two nodes if there is any intermediate node between them. So the algorithm is simple. We select a random node as a start and end point. We then create a minimum spanning tree using Prim's algorithm. In our code, we use Prim's algorithm. We can also use Kruskals. Uh, once we get the minimum spanning tree, we do a depth first search in order to decide on the order of vertices we want to visit. See, in depth first search, we may have to visit the node twice, like the way 1 to 2, 2 to 3, and again 3 to 2 and 2 to 4. But we can so in this algorithm, in this two approximation algorithm, we'll bypass this path and kind of write it as 1 to 2, 2 to 3, and 3 to 4. So this algorithm can be run in a polynomial time, but the like we said, this is an approximation, right? So it will always be less than or equal to 2 into the optimal cost. One second.
Yeah, hello. The next algorithm is genetic algorithm. Genetic algorithm comes under the class of meta heuristic. It is basically derived from theory of evolution by natural selection. This technique is generally used to find approximate solutions to combinatorial optimization problems. So to the right, we can find the algorithm depiction in the flowchart. So initially we create a random population of size k. So in this scenario, I've created a initial population of size 20. And then we have a fitness function using which we assign fitness values to each and every node in the population. So here fitness function is the objective function that minimizes the sum of cost of all edges in the path. So after assigning the fitness values to each and every path in the population, we select the best k population size. So here since the k value is 20, then we select 10 parents. And if the criteria is satisfied, we go to the next operation. So criteria here is we run a iteration of size 5,000 in this case. So unless we complete 5,000 iterations, this loop will be running on. So now we randomly select two paths from the population and perform crossover operation. So crossover operation is performed using Rowlett-Weir function. So after performing crossover operation, we then mutate the children with 5% probability. So in crossover operation, we select a random point, after which we swap the paths of two parents, and then two new children are formed. So since we had a parents of size k and children of size k, now we have total of 2K population. So out of this 2K population, we again have fitness values of these 2K population and select the best K possible paths. And then we again initiate it to initial population, and then we continuously run the loop until we satisfy the criteria, and then we finally stop the algorithm after the criteria is satisfied. So this algorithm is run on devotee state. So here we have total of 38 nodes, and we can clearly see the path that has been tracked over here. And to the below of that, we have a image of path cost versus iterations. So we can see that as the iterations grew, the path cost is continuously decreasing. So for these 38 cities, we had a total optimum cost of 9,289, whereas the actual optimal cost is about 6,500. And I have also run this algorithm on a customized data set. So the data set consists of 26 cities, and actual optimal cost is about 1,600, whereas optimal path cost for this specific algorithm, generic algorithm, is about 2,488. So next algorithm is regarding Christophoid algorithm. So this algorithm provides a solution, approximate solution, which will be 3/2 times the optimized solution. So here we can see the GIF over here, describing each and every path, every loop of the algorithm. So we initially find the minimum spanning tree using Kruskal's algorithm, and then we identify the set of vertices that have odd degree in the graph, and then we perform perfect matching to the subgraph and identify the minimum cost subgraph. And we then add these set of vertices to the minimum spanning tree, and now each and every vertex will have an even degree. Since each and every vertex have an even degree, now we can build a Eulerian circuit, and instead of repeating the same vertex twice, we shortcut them, and hence we can form the Hamiltonian cycle. Time complexity for this algorithm is big of n cube, and this is the best algorithm we have till now to perform this operation. So these are the results. This slide gives a summary of all the algorithms, and we can see the minimum distance, time complexity, runtime advantage, and pros and cons. So for the naive approach, we will only run for 10 cities, since it takes a lot of time to run 28 or 36 nodes on naive approach. All the other algorithms are run on the same data set, which contains 38 cities. So the optimum cost is about 6,000, and we can see that nearest neighbor is very close, and the third column shows the deviation from optimal solution, and looks like genetic is worst of all, but Christopher's is the best solution because this is in the bound of 1.5 times optimal solution. And we can see the complexity of naive is big of n factorial, and greedy n square log n, nearest neighbor n square, approximate algorithm 2 approx n square, genetic g of nm plus mn plus n. Here g is the number of iterations, m is the number of nodes, n is the population size, and for Christopher big of n cube. My friend Rajesh will be explaining this part.
Yeah, so this is the computational time versus, the number of nodes graph. So as you can see, since the country we took, Djibouti, has like 38 cities, we just kept the time computational analysis. See, greedy or brute force will is of n factorial time, right? So once we reach the 10th node, the time complexity is going to skyrocket. As for the genetic algorithm, it's based on the number of iterations, g into mn plus and so on. So it also have little high time, it also takes little high time. The rest of the algorithms, greedy, Christopher, nearest neighbors, and MST with primes, these are kind of running in big of n square or n cube time, right? So these they kind of follow the same trend. The polynomial time algorithms follow the same trend, as well as Christopher. It has little fluctuations and the time complexity is n cube. So as for the limitations, we experimented all our algorithms on Djibouti country, but there are like many other countries in the dataset link we had given. So uh, we want to experiment on our algorithms on all of the countries, but we couldn't get enough time. Also, if you had seen the results here, nearest neighbor gave the best minimum, nearest optimal solution. But the problem here is that nearest neighbors will have a fail case where if there are many outliers in the data, then the nearest neighbor algorithm may fail. So for that, we had to rely on some custom generated data in order to explore that fact. And there are also many algorithms like Taboo says, simulated annealing, branch and bond, link, Lin Kernighan, and many others. We couldn't get enough time to explore all of this. However, as a future work, we want to keep most of our efforts on this Concord TSP solver algorithm. This is basically a library which is written in ANSIC programming language. It has over more than 700 functions that allows user to work on TSP problems in their very own way. It is currently the best solver for TSP-like solutions. So it has much research scope to it. Like for so we want to explore more on it. And as for the conclusion for any given scenario, based on the time complexity, the proximity to find best solution, and the input size, uh, our from this project, we can recommend a better algorithm for the given requirements. For example, if the number of nodes is less than 10, then obviously go for the greedy algorithm. If you need a simple implementation and a fast algorithm, then go with nearest neighbor. Or if the input data is large and you still want the best possible solution, then go for Christopher solution. And if there are no outliers, then again you can go for nearest neighbor heuristic. So this is the end of our project. Thank you.